Okay, I think I'll begin. So actually, I'm going to focus on SIOS valuable contribution to operational weather and sea ice monitoring around Svalbard in the Arctic. So I'm not going to only focus on sea ice, but I will also talk a little bit about our weather services here as well, because I think that this is very relevant to this conference. And my name is Penelope Wagner. I'm a researcher here at the Norwegian Ice Service based in Tromsø. So I'm going to first talk about the importance of Svalbard to Norway's area of monitoring, which is what we call Met Area 19, and then go into a little bit about the weather and forecasting and the Norwegian Ice Service and how the observations based on Svalbard are relevant to our daily operations. And then I'm going to go into talk about some of the recommendations from our current EU Horizon 2020 project, Kepler. And then I think we'll close out with looking at the future activities that we're going to expect in the Arctic and some of the needs for the observing systems. Okay, so hopefully this is still clear. So the importance of Svalbard to our area of monitoring. So you can see in this gray, in this red box to the bottom right, we're responsible for monitoring Met Area 19, our areas between Greenland and Russia. So this is a very large part of the Arctic. And our office here in Tromsø, also called Værvarslinge, we provide daily routine operational information, and this supports the global maritime distress and safety system that's mandated by the World Meteorological Organization and the International Maritime Organization. So this means that we're sending out navigational warnings, weather forecasts, weather warnings, search and rescue notices, and similar information for ships. And this is to support safety of navigation and to preserve life and safety. So I think you're all well aware that this is one of the busiest areas of the Arctic for marine traffic and aircraft overflights. So this means we also have a lot of different types of end users. We have those who live on the land, so those who live in Svalbard and the eastern part of Greenland, and we also have the ship operators, so the fisheries and polar tourism, leisure ships, and then of course all the ships that are coming from the Northern Sea Route that are going into our area. So we have our users vary in expertise and their activities, and so we need to provide routine information that is easy for them to understand and access. And of course, Svalbard is one of the jump-off points for research and operations into the Arctic, and it also acts as a cultural heritage. So it's for our original Norwegian polar explorers and also a lot of these trapper cabins. So you could see that I want to illustrate the importance of observations at the Norwegian Meteorological Institute. So you can see on the left-hand side that our research, our aim is to translate our research into services, and this is driven by curiosity. And so you can see the schematic on the right-hand side where our observations are placed. They're fed into models and data, product development, and forecasts, and this is then disseminated to our end users so they can make informed decisions. And so I'll just give an overview of some activities for our weather forecasting. The map on the top, you can see where the X's are. These are all of our automated conventional observation stations all around Svalbard. And then we actually have manned stations in our areas of Hopen, Fair Island, which is also Bjørnøya, and Jan Mayen. And so these manned stations are very crucial for our search and rescue operations because they often encounter foggy conditions. And then so we really rely on observations from our highly skilled personnel because they interpret a lot of these complex weather and sea ice situations that are not possible with a lot of these automated systems so far. And also, Jan Mayen and Bear Island are in the low pressure alley. So this is actually between where the North Atlantic Ocean that goes into the Barents Sea. So this plays a central role in the forecasting. And you can see a schematic, the figure on the right-hand side that illustrates this very nicely. The yellow and orange bright colored spots is where we're seeing the cyclone density for this area from 1979 to 2016. So you can see that this area is the low pressure alley. So this is very important for us. And then these are also entry points for pressure systems into the region. So at MET, we have the AROME Arctic weather forecast model, which is updated every 3rd hour. But the future plan is to have it more frequent. So every hour updates at 500-meter resolution. So we can really monitor some of these low pressures a lot better. And I want to show you, this is an illustration of the WMO Integrated Global Observing System, the WIGOS data monitoring system. You can access this at this website down here. Oops. Below the image. But this is where you can actually see the density of observing stations. So you can see that conventional data coverage in the Arctic is quite sparse, but you can see it gets a lot more and more heavily populated in the mid-latitudes. So I really want to stress, though, that frequent and reliable data coverage is really critical for global, regional, and national weather forecasts and climate projections. So the problem is that, you know, we have very low density in the Arctic, but this is counterbalanced by the fact that the Arctic particularly is observed by the low Earth orbits, so the LEO, or polar orbiting satellites. So there's a high density of these satellites in these areas, which is great. But the issue is that there's still a global need for observations. So despite the fact that we have all these great satellites, and we're even going to rely on some of the new generation of satellites, so the nano satellites, it's very critical that we still have a lot of these conventional observations, particularly in the areas of the Arctic. So in general, the atmosphere has no horizontal boundaries. So when you're trying to independently model these areas that don't have a lot of observations, it's going to fail. Whether this is going to be weather forecasts, whether it's sea ice. So the lack of observations, this limits our ability to understand and predict the weather, both on the climate and weather and sea ice, locally and globally. So the issue is that the lack of observations at the high latitudes, they can result in uncertainties elsewhere. So when you initialize a lot of models I mean, if you don't have a lot of observations, then this will initially lead to poor quality of the model data locally, and over time this spreads globally. So of course, again, since we do have a lot of the satellites, this helps to kind of augment these areas and give us a lot of information. And this is helping to be resolved in the future, but I think we also need to be very honest that we are unable to put out buoys all the time if we want to get more surface observations. The Arctic is primarily covered by water. We can't deploy weather balloons every tens of kilometers. So this is just historically difficult and expensive to monitor these remote regions. Despite a lot of the satellite coverage we have, let's go back down to the surface, because it still applies to when we're talking about sea ice. So since most of the Arctic is covered by water, the problem is that you have a blanket of sea ice that's covering the rest of it, and this changes throughout the year. It changes regionally as well. And so this prevents us to be able to put out routine observations and really understand a lot of these oceanographic parameters. This limits our ability to fully understand how the thermohaline circulation is affected in this area, and then really make accurate assessments of tipping points and how the Arctic is going to change. So the problem is that we actually have to rely on forecasts for this, but a lot of the uncertainties in forecasts, particularly in the spring and summer seasons, where most of our users travel and work in these areas, the high uncertainties in these, and maybe the lack of understanding on how these can be applied, really impacts the way our users can understand these and make informed decisions. So I'll just provide a brief overview of what we do with the Norwegian Ice Service. So our main area of focus, we monitor the same area between Greenland and Russia, but our main area of focus is looking at ice conditions around Spitsbergen, and also Hopen and Bjornoya, And then we also have to keep an eye on the Gulf of Bothnia, the Baltic Sea, and then some areas in the southern Norway for when they're actually ice infested. And then our additional areas of analysis are going to be on the eastern part of Greenland, which we share with the Greenland Ice Service from Denmark and the Kara Sea. So our resources for ice detection are mainly satellite-based. We have very little in-situ observations that we can use. So we primarily use synthetic aperture radar from Sentinel-1, RadarSat-2, and then in special circumstances, the Cosmos SkyMed, which is using the X-band, whereas Sentinel-1 and RadarSat-2 is using the C-band frequency. And when there is no cloud cover, or when we can actually get good images, then we can use optical imagery. That's the Sentinels 2 and 3, the Vickers and AVH-RR. And then for areas that a lot of our users don't necessarily travel, we'll augment a lot of this high resolution data with lower resolution passive microwave from AMSR-2 and sometimes the Cryosat-2 in winter, if possible. When we do have in situ observations, though, we actually get sea ice information from some of our med stations, from Hopen and Bjørnøya, sometimes Jan Mayen. And then we also get reports from travelers around Svalbard fjords because we actually have a really close interaction with those who live around these areas in Svalbard. They can call us and they can give us information on where the ice is, or if we're incorrect, but we try to have high precision on how we cover the ice in the fjords. And sometimes we can get reports from vessels and aircraft by using ship-based sea ice observation, the Sea Ice Observations Program, which is called Ice Watch. And the software is SESS, and we host it at the Norwegian Ice Service here in Tromsø, and I'll talk a little bit about that in a bit. So these two graphs on the right-hand side, these are a good illustration of our typical winter sea ice coverage around Svalbard to the left, and then to the right is our summer sea ice. So you can see that this is very dynamic, and that this is primarily first-year ice. It's wind and current driven because it's first-year ice. So it's really vulnerable to a lot of the environmental conditions around Svalbard. I think we all know how dynamic it is. So during the winter and spring, we'll see that we have a lot of ice north of Svalbard. You'll see a lot that's going to come around to the eastern part, but then we also see the ice and fjords on the western part where most of our users live and travel. And so during these times, our analysts, they study different types of ice around the Svalbard. And so they're looking at ice and fjords. They want to make sure that those who rely on ice being there, those who are driving skidoos over, that this information is reliable, but also that the concentration all around in the fjords, that it's present, because you'll see a lot of ships that are going to the northern part, and they want to make sure that they want to know what kind of ice is going to be present, or whether or not there's going to be a danger of ice that's going to be ejected from the north into these fjords, which is going to, cause a big problem with their ships. So within the ice in the fjords during the winter, it's primarily thin ice, thin fast ice, which is approximately less than 30 centimeters or so, but this can include a lot of hummocks and ridges, and then sometimes old ice is present in these areas, and that's coming from the Franz Josef Land. So we've seen that every so often. It depends on how this ice is affected. And then the summer and fall, we're actually looking at how the melt and freeze, like whether or not the change of the ice is usual or unusual. So we're looking at how is it melting or how is it freezing up. There's the sea ice minimum and the maximum that we also follow, but this is like on the Pan-Arctic climate scale. But of course, we're looking at these on a regional scale, and those can be very different than what we're seeing on the climate scale. So I just want to show some examples of some of the challenges our analysts encounter. And I want to say that our ice service, including all ice services, are still fully they still provide routine products manually. There's no automation or semi-automation in any ice services because there are inherent caveats within these satellites, within the current satellites, where particularly in spring and summer, the snow cover on top of the ice really prevents us to be able to accurately monitor where ice is, because the melting snow has a lot of the same signatures as open water. So we can really underestimate where the ice is. And so what our analysts do is you can see the different quality of even these very high resolution images. The top one is Sentinel-1 SAR, and the second one is RADARSAT-2. They're both using the C-band frequency, but you can see that in the Isfjorden, we're showing different signatures of sea ice. This is also related to wind and how thin the sea ice is. And you can see on the Vickers to the left that you can see where the ice is in the fjord. So we really rely on the expert input from our analysts because they follow the sea ice every day. They understand the regional and seasonal variabilities. And this is incredibly invaluable for us to be able to provide a very high precision, high quality daily product. And they put these into the routine charts. So similar to how EAR puts out weather information on a daily, hourly basis, our analysts put out these ice charts for ship navigators and those who are relying on this information for their safety. Here's another image of the polynya that's developed in Nordenskiöld. Now, this is a very critical area as well for all users, for whether it's tourism or research, because people will drive ski-doos over here, and this is also a really popular lookout point for wildlife. But you can see that from the Sentinel-2 and the RADARSAT, Sentinel-1 and the RADARSAT-2, that we're seeing different signatures of sea ice. And again, these are compiled and converted into these very easy to read images for users to the right. And so when our analysts have a difficult time really trying to detect some of the sea ice, then they'll use the webcams, these webcams that are located all around Svalbard. These webcams are very important because we can see where the ice is in the fjords. They can also talk to those who live in the area and get some confirmation. So, but I guess the problem is that we don't have a lot of these located all over Svalbard, so we're quite limited. But these are a very good resource. And next, when possible, we also try to use images and observations from ship-based observations. This is using our Ice Watch program. We acquired this in 2019. It was originally developed at the University of Alaska, and this has been used. You can see we have archives of sea ice observations that going back to 2007, and it just keeps growing and expanding. This also includes observations from not only research, but polar tourism, some citizen science, and also those who are on operational vessels. So we're hoping to really expand and build upon this, and you can go to the website on the bottom there. So now I actually want to talk about, now that we're talking about end users, I want to talk about our EU Horizon 2020 project, which is the key environmental monitoring for polar latitudes and European readiness. So this was originally inspired by the Copernicus User Uptake Review, and this was primarily focused on raising awareness for the Copernicus program, informing and educating Copernicus users with user needs and to let them know what user needs are, encouraging Copernicus users in the public and private sector, and enabling access to the data so we can really increase the uptake of Copernicus data and information. But most of the project has actually been really doing a very robust assessment on the identification of research gaps regarding the integration and assimilation of the products that are already available in Copernicus, and also look at what needs to be done for improved sea ice mapping and forecasting products in the services. And this is going to be based off of user needs. So you can see that the users are at the center of this orbit. So this was purposely done, that we actually wanted to center all the work around what the user needs were. So this was focusing on the maritime user needs, land user needs, and those who are developing products for climate and weather forecasts. But I'm actually only going to focus on the maritime needs for this presentation, because I think this is more relevant to the SIOS at this point. So you can see that project partners, we have about 18 project partners from 8 different countries. So this includes Copernicus Copernicus service providers, Those who are working on terrestrial monitoring, so permafrost, snow cover, search and rescue. Those who are working with maritime monitoring, and all of the European operational ice services are included. And then, of course, the forecasting development. So this is a quite comprehensive group. And here is a schematic of the organization of work. So you can see, again, the stakeholders are on top of the whole schematic, and then their user needs are fed into all the different work packages in the requirements. So we're looking at all these different user needs and using that to assess how the polar regions provisions in Copernicus services. So that's all the products that are in the Copernicus services that are developed for the polar regions. How are they, how well are they actually supporting these user needs? In work package 3, looking at the identification of research and capacity gaps, but this is also mainly focusing also on what are the current satellites out there, what is their capability, and what is the situation with in situ measurements and observations, and how are those used? And the last one was work package 4 was primarily focused on sea ice mapping and forecasting. So the sea ice mapping was for what are the ice services requiring in order to integrate more Copernicus products developed for Copernicus, and what are the needs for sea ice forecasting. And so at the very end of this work package 5, we're currently working on this right now. This is the end-to-end operational system, which is going to be a full comprehensive recommendations from this project that is going to go to the European Commission. So we're ending this project right now, but so we're like kind of in the thick of it. So if I could actually sum up from this project the recommendations for improvement in one sentence, it would be that products should include levels of certainty, taking into consideration inherent seasonal and regional characteristics and limitations in order to be more useful for end users. So therefore, that means that products need to be very clear, easily understood and accessible, and most of all, relevant. Because you can see that if you look at the schematic from the spatial, comparing the spatial scale with the time scale, those who are working on an operational level, who are making tactical decisions, they're working on a much more higher spatial and temporal resolution, whereas those who are working on strategic or voyage planning can kind of overlap between that, but they can work on a little bit longer medium time scales versus those who are working at much longer time scales that are working policy and standards and regulations. So we have to keep all of this in mind when we're developing products and looking at how they can be used for users. Now, all users can work on all these different scales at different times, but I think that it's really important for us as information providers or product developers or researchers to know where these differences lie. So a summary of the recommendations from work package 1, which is subtask 1 in the maritime user needs. The land user needs were actually focused more on indigenous communities on the northern part of Norway, Sweden, Finland, and Russia on the mainland, and not so much about those living on Svalbard. So I'm only going to include the maritime user need on this one. And overall, what was a consistent recommendation and feedback was that we need consistent and well-defined terminology. This was actually taken from European Commission, European Space Agency reports over the last 10 years. Internal surveys, current surveys that were done during the time of the project, and also many different workshops that incorporated different types of end users and maritime users that work on multiple different scales. So all of them unanimously agreed that consistent and well-defined terminology is necessary. So how we refer to products as high resolution or near real time or operational or short or long term needs to be very clear, because the ice services and ice information, that is not the same as information that you would use for climate monitoring. So this is very important. And then for the current products that we do have, there's for a long time, there's been a request for improved spatial resolution of satellite-derived sea ice products and forecasts. So really at the hundreds of meter scale. And further parameters for future monitoring for safety, they want sea ice type deformation, ridging, accurate ice edge mapping and coastal zones and detection of leads to be included in these routine products. Currently, a lot of ice services, they will all provide sea ice concentration, but it varies depending on how much information others can provide. For example, the Finland and Sweden, they can include sea ice types in their ice charts on a daily basis, but they have a little bit of a different infrastructure and they have a lot more regulation, and that's a main area of maritime traffic where they're in the Baltic. So this is what a lot of the users request, and then of course better access to high bandwidth communications at high latitudes, and data information provided in graphics or text format, so very accessible, very easy, and very easily understood. And then what they also want is iceberg products that can display individual icebergs, ideally with all false targets filtered out. Even with the current high resolution satellites that we have, it's very difficult to monitor icebergs because they have a lot of the same signatures as ships and other different types of targets that you'll see in the ocean. So this is, to get a lot of these smaller icebergs, it is very difficult. We can monitor these very large icebergs in Antarctica on the multi-kilometer scale, but that's not something that we can, of course, do in the Arctic. So work package 3, so focusing on the in situ and capacity gaps. One of the main recommendations that Europe lacks a coordinated collection of in situ data in sea ice covered regions. And again, it's just very difficult to routinely observe and provide observations for material that's moving all the time. So a main recommendation was that the citizen science activities should grow and aid in collaboration and validation, and that the Copernicus should have more of a coordinated role in in situ observations for validation and quality control of products. Am I almost going over time? Sorry, Shridhar. I only have a few more left, actually. So this is also, again, supported by the recent Arctic Council PAME report. This, one of the main recommendations to aid in navigation and meteorological forecasts is that the Arctic marine infrastructure is needed to, improvements in the Arctic marine infrastructure is needed to enhance safety and environmental protection. So examples of this infrastructure is better ice navigation training, navigational charts, communication systems, and accurate and timely ice information for ice centers, among others. And then also another recommendation from this report is that industry helps to contribute to these observations, so that we should actually increase our observations with the meteorological, oceanographic, sea ice and iceberg observations from industry, and so that there's a system, that systems need to be developed to support this type of coordination. And for the sea ice forecasting, one of the main recommendations is that we need to improve assimilation of data using appropriate short and long-term data inputs. At longer lead times, some of the biased improvements might come from improving the model quality, but when we're looking at short-term sea ice forecasts, improvements in data assimilation is necessary. So we actually need to assimilate the correct input data. We need to assimilate the data that is representative of the ice conditions at the time. And also areas that are covering things like the ice edge, ice in the coastal zones, in the fjords, and hopefully areas of fleets. And then also that we need to improve the provision of observations to allow robust collaboration and validation. So this means that a lack of suitable observations, this prevents forecast models from initializing these parameters. Of course, the more accurate these forecasts are, the better we understand the system. And that the probabilistic methods and new classes of models to improve spatial resolution. So things like ice convergence can be used as a proxy for difficult ice conditions. And primarily that sub-kilometer scale sea ice observations should be used for now for short-range sea ice forecasting. And so some of the main key find these recommendations for Earth observation for Copernicus in situ products and services. So the current state of the products is that an independent scientific audit on the quality information documents should be done. So this means that an external body needs to go in and independently audit these to make sure that this is all standardized and that we're all following a certain compliance. And that there should be a prioritization of CalVal in situ measurements to reduce the identified uncertainties in some of these products. And also developing a framework whereby Copernicus services can better use the European polar research assets provided needed for CalVal opportunities. And this will help to enhance the opportunities for a broader European polar community. So this also leads into a main thing is actually ensuring independent quality control of services and products now and in the future. And this also includes for when we get, when the new generation of satellites do become available. And also encouraging where possible, publishing in peer-reviewed journals of a more academic version than the quiz. So not just technical documents, but really encouraging more peer-reviewed types of publications. And so also the last one is providing recommendations from Copernicus to the European research community. So this will actually help to improve the accuracy of CalVal data for a particular product. And right now, this is what the end-to-end operational system looks like. In Work Package 5, you can see that we're going to consolidate all the recommendations from all the work packages into this system. And this is going to actually show how a lot of these products can be better used for these downstream services. And so what are we going to expect for the future of Med Area 19? With the Arctic amplification, it's going to become more important than ever to have accurate predictions of the Arctic region to support the safety. We're going to expect a lot more dynamic changes in the weather. Certainly in the sea ice, we're going to see a lot more first-year ice developing that's going to potentially be more dominant than the multi-year ice. And then, so it's very, very, very important that we make sure that the satellite-derived observations and products are still grounded in reality. This also will help us to have an accurate record of how the climate is changing. So when we're looking at forecasts to directly support end user activities, they need to have the relevant assimilation in them. So recently, actually, so last year, the Congress of the UN's WMO agreed to establish a global basic observing network. This is a great idea, but the problem is that achieving something like this requires commitment and a substantial investment from these countries, from the member countries, and the political will to share this type of data. So, but this is a good step forward. And with the weather observations, even though we actually have a really good, robust system in place with the weather stations and the weather balloons, we're still going to have a challenge of having new stations to monitor sea ice and open ocean. So there is critical need for these types of observations. And with regards to sea ice observations, it will require a more Lagrangian routine type of method. So it's going to be either ship observations or buoys in order to really capture the scale of sea ice monitoring for sea ice observations that we're going to need. And this is being addressed by the WMO Global Cryosphere Watch at the moment. So I guess I want to close our presentation on then how does SIOS fit into these other global observation systems, and then how can the Global Cryosphere Watch cryonet sites and stations help to link in with the SIOS?
Okay, thank you very much for the opportunity to talk about CIRFA at the SIOS conference. And I will first start by acknowledging my co-workers who has actually produced much of the work I'm going to present. First, let me give some overview introduction about the center. So CIRFA stands for Center for Integrated Remote Sensing and Forecasting for Arctic Operations. Our vision or objective is to develop knowledge and technology for environmentally safe industrial operations in the Arctic. So we are basically focusing on developing methods and technologies that can reliably integrate and analyze remote sensing data from multiple sensors. In this regard, we hope to improve surveillance capabilities in Arctic operations, improve assimilation methods and forecasting services, and also we aim to improve understanding about the important geophysical processes that's going on in the Arctic. Focusing on Arctic remote sensing puts some requirements on what we are working with. And some of these requirements are related to which sensors are usable. We need to have sensors that are independent of weather and light conditions. We need to be able to monitor multiple scales at high resolution and have frequent imaging of the area of interest. And there are some conclusions that can be made from this. We need to work with synthetic aperture radars. We certainly also need to combine platforms to get the temporal coverage that we want. And we also need to combine sensors in order to get as much information as possible. CIRFA has 3 application-oriented work packages, and I will concentrate in this presentation on these applications. But I will basically focus on the collaboration, I would say, or how we can combine the work that is going on in work package in the application-oriented work packages with work package 5, which is addressing numerical modeling. In general, we could say that integration or integrated remote sensing in CIRFA's respect is to combine the information from the different application areas and the supporting work packages. But in this presentation, I will focus on the combination of remote sensing and numerical modeling. So CIRFA basically is physics-based in the way we try to extract information from the satellite data. That means that we have a geophysical model as a basis for the extraction of the information. So a workflow may look like this, where we we have the satellite observations, we have some pre-processing, but we use the geophysical models and prior information or human interaction to extract the information, or to help extract the information. But in some cases, there are ambiguities where numerical models can help select correct solutions. And in other occasions, the numerical predictions are themselves the information that the user would be interested in. In CIRFA, we have also users as partner in the center. So in the process of developing services and information products, we are trying to strengthen this feedback loop from the end users back to the analysts in order to improve the algorithms that we are working on. So I will go through some examples here. And the first one is about extraction wind information from synthetic aperture radar. So we have a Sentinel-1 image, for example, and we from that image we can extract the radar cross-section. And the geophysical model then relates the radar cross-section to parameters associated with the wind, like the U10, the direction of the wind. And this model also takes into account the frequency of operation, the polarization, and the incidence angle of the SAR. And the output will be a product like a map like this, where you can see wind speeds. But in this model, there is when you try to optimize this estimation, you will have ambiguities in wind direction, where you can use numerical models to solve these ambiguities. And to see more of the advantage of using the SAR, here we have the intensity image from the Sentinel-1. We see the wind field that has been estimated from the SAR image. And you can see that the wind field pick up some of the details that you can easily see in the SAR image. We also have the sea ice in this image, and sea ice will confuse the algorithm. So this red part up here is related to the presence of sea ice. And here, by combining the algorithms that are working on sea ice and the people or the algorithm that working on wind retrieval, we will be able to solve this problem. If you compare the wind from the model with the wind from the SAR, we see that the SAR has more details in the wind field. And that is the aim of using SAR for this application. And when we add the direction, we also see that the direction of the wind field is more detailed, described by the SAR algorithm. Another application from the MetOcean work package is estimation of ocean current from SAR images. This is based on basically estimating a Doppler shift from the singular complex SAR data. This Doppler will consist of several terms. And what we are interested in is this term here. So in order to be able to extract that component of the Doppler field, we need to estimate all the others and isolate that particular component. We have defined the different terms here, and those that are not related to the physics can be estimated if you have land in the scene. So we will show, and we have been working with situations at the coast of Finnmark, where we have where Norway has some HF radar systems operating, and here we are able to compare wind current retrieval from synthetic aperture radar with what the HF radar gives us. And we can see that these strong currents here are detected correctly from the SAR image. Let's go to sea ice, which is another large activity in the center. For sea ice remote sensing, we are trying to develop algorithms that can automatically classify sea ice types which can estimate sea ice drift, and we also are involved in trying to detect the icebergs freely drifting both in open ocean and in sea ice. So in this work, we need to collect data. We need to collect in situ data and validation data. And this view graph actually shows some of the data sources that we use in developing these algorithms. So how can we classify sea ice from SAR? Well, first of all, different ice types, as was presented in the previous talk. There are many different ice types, and let's see how the different ice types manifest themselves in a synthetic aperture radar image. Basically, the internal structure of ice, multi-year ice and first-year ice, is different, and this internal structure of the different classes manifest themselves in signatures in the SAR signal that can be used when we do the classification. So this is what we try to exploit, and the work then is to develop algorithms that extract different classes based on understanding of the scattering mechanisms. If you look at the SAR image of sea ice, we see that we can see quite detailed structures, and some of them are easily interpreted, but others are difficult. But one of the challenges with sea ice is that it's dynamic, it changes, and it's ambiguous. So it's not such that one signature necessarily refers to one specific sea ice type. In that respect, we can improve our understanding by looking at other sensors. Here's an optical image of the same scene, and we see quite different things in the optical image. And by combining the SAR and the optical image, we can understand more about the signatures that we have in the SAR image. This is another example, and we see that an optical image may not be possible to use for sea ice classification, because it only, if it's covered by snow, we don't see the details of the ice. So here I would like to focus on two problems that are being addressed in CIRFA. And these are the dependency of the signal on the incidence angle and the noise pattern that is complicating the interpretation of Sentinel-1 SAR images. So in CIRFA, we have tried to address this in a quite a different way by integrating these dependencies into the algorithm, instead of doing this or applying pre-processing in order to solve these challenges. So let me try to explain how this works. So I got some problem here. Okay. Okay, so So if you look at the image to the left, we see that different ice types have different dependency of the incidence angle. We have water, we have multi-year ice, and we have first-year ice as the blue, red, and green lines that you can see in the left part of the image. And if you look at the histograms, if you apply a Bayesian technique to classify the images, we see that the histograms overlap. So the statistical distribution of these will be mixed, and it will be difficult to classify these into separate classes. If we apply pre-processing in order to correct for this incidence angle dependency, we can correct for one class, but we cannot correct for all because they have different dependency of the incidence angle. And even if we are able now to separate the green and the red classes, we are not able to separate the red and the blue. So our approach here is to integrate the dependency of incidence angle into the statistical model, and we apply a mixture model for the data, and we see that at some incidence angles we are able to separate all the classes. And this is the basis for the algorithm. So when we apply these algorithms to data, we can see quickly that it has some effects. This image here shows a segmentation based on non-corrected image. And we can see that we get banding in the image across the incidence angle, which is not related to the physical classes, but it's related to the incidence angle. So by integrating the incidence angle into the classification algorithm, we are able to get a more clean and more correct segmentation of the image. We are able to separate the classes more based on their physical properties. And this can simply be used also to separate ice and water. We see here a scene where we have water here, so we see red and the yellow are different classes in the water. And we have sea ice, and we can also see that there are some open leads within the sea ice. The other problem is the noise profile that has been very difficult to remove from the Sentinel-1 data. The image here to the left shows that here we are working on a noise corrected data given from ESA, and the red line or the lines show the incidence angle of different classes. As you can see, there are still curved curvatures in the noise profiles that has not been removed from the images, and this will cause errors when we perform the classification. So our approach is to work in the same way as we do for the incidence angle, is to integrate the noise as a part of the model, and this shows that this will improve how the profiles of the incidence angle dependencies follow the data. And we are able to pick up some of the curvatures that actually are in the intensities. This is showing the same thing. This is work that are in development. but we hope that by doing this integration here, we are able to also perform better and more correct correction of the data. By doing this pre-processing and where we withdraw the noise profile from the data, we can also create negative results, which is physically not correct. So we think that our approach is more neat from a mathematical point of view. And we have examples where we see that this is providing good results. So the aim of our work is to be able to produce high-resolution sea ice map automatically generated from SAR, and we can use them to also or extend them to a large scale. So we have available now a system to mosaic together classified images and get a whole Arctic view of the sea ice conditions. So let me go then to the final application, which is oil spill remote sensing. And in the oil spill remote sensing that we are working on in CIRFA is first detecting oil slicks on the ocean surface. But most difficult is the problem of characterizing the oil slick. That means finding is this an real oil slick or is it a lookalike? And a final problem that we are addressing is drift modeling. How does an oil slick interact with the ocean and drift? In this work, we are working closely with NOFO, which is an organization working with the oil or owned by the oil companies for looking into the pollution that might occur in oil production, in connection with oil production. We have been conducting several experiments where we have been very heavily involved together with NOFO. We had one where we hired the JPL UAV SAR airplane, and with that we were able to collect data for get a time series of data over the same oil slicks, and that was very useful for testing out drift models and how the oil is behaving in open water. And also in connection with the oil spill remote sensing, we have a lot of in situ measurements being done during this work. In 2019, we had our own ship during an exercise where we released some soya oil and some real oil blend, and we were able to make a lot of observations with a German airplane, and we had a lot of in situ measurements going on. As you can see from this slide, this device up here is a device for measuring the thickness of an oil slick. So just to go back to the characterization of sea ice of oil spill, there are two physical properties of the oil of the effect of oil on water. One is that it will affect the surface roughness. The other one is that it will affect the electric properties of water. And by looking into these both these two physical properties, we can maybe be able to distinguish between lookalikes and real oil slick, and we can also maybe be able to find out where in an oil slick you have the thickest part. So the small-scale roughness of the ocean is reduced when you have a film over the surface, and this reduced roughness causes less backscatter to the sensor, and we can see these kind of signatures in the SAR-C. So the rougher the ocean is, the more signal you get back to the sensor. And in order to distinguish between different slick types, we have been looking into methods which are focused on polarimetric properties of the SAR. And here we have three different slicks, where one is a plant oil, which is simulating a natural biological fill. And we see by analyzing the data in a proper way, we can distinguish this biological film from real oil slick. This is useful for avoiding false alarms in oil spill detection. When it comes to this experiment I mentioned with the airplane, we are able to monitor an oil slick, or actually 4 small oil slicks for many hours, and we had acquisitions that lasted for almost 8 hours, and we was able to follow the slicks, and that allowed us also to look at drift models. And I will show that by tuning the models with input from the satellite data and the remote sensing data, we were actually able to quite accurately model how the slicks would drift. So in this figure here, we see that the color indicates the time, and this is where we release the oil, and you see how the plant oil is drifting, and this is the model which is showing the same pattern. And this is another emulsion where this is the release point, and you see how it developed. And it's very interesting also to see how these two slicks developed very differently, and that the models, when they were properly tuned, were able to describe this behavior. In one of the experiments we participated, we were trying to develop a system for determining where in the oil slick we had the thickest oil. So if you have a release, that's where you would like to put your effort in collecting. And this product is based on what we call a damping ratio. And the point here is that the stronger the signal is damped, the thicker we think that the oil is. And it looks like this. So during the exercise we had in 2019, this information was provided to NOFO on the fly, and they were able to use this information when they planned their operations. So this is another example where we try to validate that this damping ratio is predicting the oil thickness correctly. The other effort that we are working on in terms of characterizing the oil is by looking into methods for estimating the dielectric properties of the oil. Oil has a much lower dielectric constant than seawater, and we are trying to model how this can be extracted, this information can be extracted from the source signal. I see that I don't have time to go into very much detail on this, but I can at least show that we apply physical model for how this is how the signal is scattered from the sea, and we in this particular model we need to use the ratio between the two copolarizations in order to extract the electric constant. So this is a couple of examples where we see that determined the electric properties from the oil slick is behaving at least in the direction that we want it to do, because as you can see, the red area is where you have most oil, and in the outskirts of this slick, we have a thinner slick, and the electric property is determined by the water. And this image shows the same thing. So I'm trying to conclude now, and so my message or my message here is to say that in CIRFA we try to combine understanding of the physics of remote sensing and use this information, this understanding, to extract the physical parameters that are relevant for interpreting the SAR images. And the collaboration between numerical modeling, physical modeling, and observations is a key in the process of extracting services and information products from remote sensing. So finally, this is the partners that we have in CIRFA. It's University of Tromsø is the host. We have NORCE, we have SINTEF Narvik, we have the Norwegian Polar Institute, Meteorological Institute, NORCE Center, and NTNU. And we have these user partners. So thank you for the invitation.
As the name says, that's a report that summarizes the state of the environmental science in Svalbard. And the purpose of, or the concept of the report is to present integrated data sets over entire Svalbard, and also to connect in parameters across several spheres. In addition, other authors or have the opportunity to highlight research needs for the future and to recommend on how to address them in terms of infrastructure or data sets, etc. The SESS report is also a forum to the open sharing of ideas, which then allows an open discussion and a joint basis on how to improve the observing system in Svalbard. Potential outcomes of the SESS chapters can be new or adjusted data sets, new or improved research infrastructure or co-location of research infrastructure, and of course increased international cooperation and also interdisciplinary cooperation. The SESS report was established with the idea to make it the source of information about the state of the environment in Svalbard. It is an important tool for SIOS to convey the knowledge to the stakeholders and the public. It comes in two versions: the full report that is addressing scientists, member institutions possibly, and then we have the popular science summary that is aiming towards the policymakers, funding agencies, and the public. So with this format, we aim to include all the different groups in the discussion of the development of the observing system, to ensure that there's a synergy between the scientific investigations and the knowledge needed by the society to safeguard the Arctic environment. And contributing to the SESS report gives research groups the opportunity to actually actively influence the priorities within research or within SIOS, and with that the research environment for Earth system science. Just some facts. We have now 3 issues of the SESS report, starting in 2018. And the numbers of authors, institutions have been both increasing. The nations have been quite stable on 12, 13 nations that contributed. And you can see there's a lot of recommendations coming in, also an increase of number of recommendations. So there's a lot of good ideas and a lot of things to start working on, which we already have done. The contributions can be either funded by SIOS, or be in kind, or can be a combination of both. All chapters are peer reviewed, and there's an editorial board that decides on the content, or has the final decision on the content. As you can see, the number of chapters on the right side, we started with the first issue and 9 chapters, followed by the second issue with also 9 new chapters, but also 4 updates of chapters from the SESS report 2018. In 2020, we only had new chapters, and we had 3 chapters relate to snow observations, which then resulted that there is a joint chapter of these authors of these 3 chapters give a joint statement on that topic. For 2021, the SESS report 2021, there will be only updates. Currently we have 7. The reason for that is that we want to slow down the process a bit in order not to gather more and more recommendation, but to start really consolidating those recommendations that we have. So from this year on, we will alternate update issues where there will only be updates, and then in the next year there will be new chapters. There's also updates. There can also be updates included, but we will allow new chapters only every 2nd year. So for the 2021 SESS report, we have updates from the report 2018. There we didn't have this nice figure yet, so I would put it in here. It will be IMOP and UV ozone. The chapters will be updated. And from 2019, there's the 3 chapters: Quad, Svalbard, Sol, and Past Ice. And in 2020, we will have updates from passes in UAV Svalbard. If you want to read the SESS report and you haven't done that yet, they're available in both formats on our webpage. And the SESS report 2021 will be released during the Polar Night Week in January 2020.
So the work that I'm going to present today is based on the study that we did for the SESS report, StatMod Snow. It's not completely identical, but it's kind of an extension of what we presented in the report. So what we wanted to do was to carry out a comparison of remote sensing and model-based snow cover datasets for Svalbard, and look at the similarities and differences between the datasets, and investigate possibilities for ways we could improve the consistencies between the datasets. So this is work that I've carried out with colleagues from NVE, the Meteorological Institute in Norway, and University of Uppsala. Right, so the motivation for the work was, we know that accurate snow cover is important for the calibration and validation of hydrological models and climate predictions. There are several remote sensing datasets that for snow cover that exist, such as those from the AVHR, satellite, MODIS, Landsat and Sentinel-2. But they lack consistency with respect to the spatial resolution, and they have different periods of different time periods of coverage. In addition to the remote sensing datasets, there also are a variety of snow models which can assist with filling in gaps where these optical sensors can't provide data coverage, for example, during the polar night or during periods of cloud cover, which there are lots of over the Arctic. So there's a need to reconcile the differences between the low resolution datasets and the newer high resolution sensors to provide a long-term and consistent snow cover record. Yeah, and as I mentioned earlier, this is an extension of the early work which we wrote about in the SESS chapter, StatMod Snow. The title of that was Satellite and Modelling Based Snow Season Time Series for Svalbard, Intercomparisons and Assessment of Accuracy. So I'm only going to be going briefly through all the data sets and the results because of the time constraint, but if you want to, the work we, that I'm going to present now has been published in an article for the SIOS special issue in remote sensing, so you can find more details there. So in the SESS report, we used 4 data sets, and in this table I've highlighted the 2 differences to the work that we've done now. So basically we started to include Sentinel-2 in this work, which we have 4 years of data for, and that's the most high resolution sensor that we have for the remote sensing datasets. We have the 20-year MODIS snow cover dataset, which has a resolution of 500 meters, and then a 34-year AVHR dataset, which had a resolution of 4 kilometers. In addition to those remote sensing datasets, we had the CNR-IIA and a snow model dataset provided by University of Uppsala, which is the energy balance and snow fern model, I think, which is the EBFM, and that was like an updated data set with respect to the one which we used in the SESS report. So it covered slightly longer period and that was slightly different parameters. So for the study area in this work, we decided to focus on only the area which overlaps with all the data sets. So our Sentinel-2 dataset didn't cover the whole of Svalbard, but it covered basically the central part of Svalbard over Nordenskiöld Land. So we decided to choose this area to study to basically compare all the data sets. And in addition to this, the MODIS dataset had the best temporal overlap between all the remote sensing datasets and the snow model datasets. So for the purpose of the study, we've used it as a baseline for all the comparisons, even though it's not the highest resolution sensor. So the main objectives for this study was to start to study the temporal and spatial differences in snow cover observations. We also wanted to look for correlations and relationships between the MODIS dataset and the other remote sensing and snow model datasets. And then as an additional objective, compared with the SESS report, we wanted to look for a way to improve the consistency between the datasets. So not just comparing the datasets, but looking for ways to adjust the snow cover datasets and bring them in line with the reference. And as a last objective, we wanted to also study the effect of these corrections on the timing of snow disappearance, because this parameter is important for in ecological systems, such as the timing of green up and for the timing of runoff and water availability. So before we could do the comparisons, we had to process the data such that all the data sets were resampled to the same grid. So we basically resampled the snow model datasets and the AVHRR and Sentinel-2 datasets to the MODIS grid at a 500 meter resolution. And then what we did was to produce a time series of the land averaged snow cover fraction from binary snow cover extent maps. So this is basically the average snow cover over the whole study area, excluding water and glaciers. So for the products which weren't already binary snow cover maps, such as this SWE product from the EBFM model, what we did was to apply a threshold to the SWE data to derive a binary snow cover extent. And this was basically, we derived this threshold by trying out a range of different thresholds and performing a linear regression on the data set, so we could find where there's best agreement between the MODIS, the reference data set, and the snow model data set. And for the Sentinel-2 data, which was originally maps of the normalized difference snow index, we applied a threshold of 0.4 to obtain the snow cover extent. So this is basically a figure showing a comparison of the land average snow cover fraction for all the years, the MODIS years. So what we noticed from just qualitatively, there was basically a higher summer minimum snow cover fraction in the AVHRR dataset, which is the 4 kilometer dataset. And for CNR-IIA, which was the snow cover fraction dataset, we saw that there's a lower summer minimum snow cover fraction. And for both snow models, there was a tendency to, we saw a tendency to a slower increase in snow cover fraction during the autumn. So what we did next was to basically produce a scatter plot of these time series of the snow covered fraction for each data set, which is shown here. So basically we've got the AVHRR data set up in the upper left hand corner, Sentinel-2 in the upper right hand corner, and the 2 snow models along the bottom. So in addition to plotting out the, making a scatter plot of the snow cover fraction, we separated the data points into the spring and summer period when the snow cover is decreasing, and the autumn period when the snow cover is increasing again. For the 2 remote sensing data sets, we didn't see a difference in the relationships between the summer and autumn snow cover fractions. And in general, we found that the AVHRR data was substantially greater than the MODIS snow cover fraction at intermediate snow cover fractions, whilst for the Sentinel-2 data, we found that the MODIS snow cover fraction was up to 10% greater than the Sentinel-2 data, which was the higher resolution sensor. For the 2 snow models, there was a difference of up to 10 to 15%. So the snow models were up to 10 to 15% greater compared with MODIS, sorry. This was for the spring and summer snow cover fractions, whilst for autumn there was a much more different relationship. We found in general that the autumn snow cover fractions from both snow models was less than the MODIS, which we saw from the temporal variations. So another thing we did was to look at the geographical differences between the data sets. And in this figure, I've shown the average difference in the number of days with snow from each data set for the whole study area. And basically the color scale that I've picked here shows that for the blue colors show that the data set has more days with snow compared with MODIS, and the more red colors indicate fewer days with snow compared with MODIS. So what we noticed from this was that for the ABHRR data, there was generally more days with snow compared with MODIS in the lower lying areas. Whilst for Sentinel-2, there was generally less days with snow compared with MODIS over the whole study area. And for the two snow models, there was generally less snow at low elevations, but for the EBFM data set, there was a tendency towards more snow at the higher elevations, especially in the northern part of the study area. Yeah, so basically this figure is sort of a summary of the geographical differences. And what we've shown here is the altitude distribution of that mean difference in days with snow for the different data sets. So as you can see here, for the ABHRR data set in blue, there's tendency to more days with snow below 200 meters above sea level, and then fewer days with snow at higher elevations, whilst we have the opposite trend with the EBFM, the snow model dataset. So that shows that there's an underestimation of snow at lower elevations compared with MODIS, and more days with snow compared with MODIS at higher elevations. And for Sentinel-2 and CIRFA, there was fewer days with snow, irrespective of altitude. So what we tried to do next, which was basically the extension of the SESS study, was to make an adjustment to the land averaged snow cover time series to bring them more in line with the MODIS dataset. So what we did first was, because we've implicitly assumed that the Sentinel-2 sensor has a higher accuracy than MODIS, we used the spline fits, or like the fits that we made to the dataset, which I showed earlier. We used those to correct the MODIS dataset first, and then from the corrected MODIS dataset, we obtained new relationships with the other datasets and used those to correct the datasets. So the effect of this was basically to make the bits more linear after the correction. So this basically is take away the bias in the datasets that we saw earlier. So whereas it was for the ABHRR dataset, whereas it was earlier some tens of % greater than MODIS, the corrected dataset is now more in line with the MODIS dataset. And the same goes for the two snow models. So using these corrected time series of the snow cover fraction, we wanted to look at the effect on the derived estimate of the first snow-free day. So for the first snow-free day, we've basically taken this to be the point at which the snow cover fraction first decreases below 50% and remains there for at least 5 days. So for both the original data sets and for the corrected time series, we've estimated this first snow-free day. I haven't showed the estimate of the first snow-free day for the uncorrected data sets, but only for the corrected data sets. But what we found basically was for the when we used the original data sets, the AVHRR, CNR-IIA and EBFM data sets were up to 15 days earlier than, 15 days later compared with MODIS. And then after correction, there's much better agreement between both the MODIS dataset and the other datasets. For the AVHRR dataset, we had a 34-year time series. So what we wanted to do with that was
wrap up. You're running out of time now.
Oh, oops. Okay. Yeah. So for the 34-year time series, we found basically that the effect of the correction to the data, the time series, resulted in a first known free day, which was not only 2 weeks earlier, but also the trend was slightly, the advance in first known free day was slightly weaker than if we'd used the uncorrected data set. So basically, this kind of indicates that some care must be taken when interpreting trends derived from the lower resolution data sets because of the effect of the overestimation of snow cover. So what we want to do in the future is to ideally be able to do these corrections at the pixel scale and not for just the land average snow cover fraction, and also to try and use the results to improve the discrepancies in the snow models, and yeah, to improve the snow models basically. Sorry, that's basically it.
So what I'm going to show you is a summary of what we have done for the last SIS report, and I would introduce what we are going to do in the next future. So the idea is to contribute to the Svalbard scientific community, having an overview about the time-lapse cameras available in the archipelago. This activity was named PASSES and was contributed by CNR, Italy, and Norwegian Polar Institute, Institute of Geophysics from the Polish Academy of Science, University of Tromsø, and the University of Oslo. The idea is to find a way to solve a problem concerning the gap between manual observations and satellite observations, and we plan to evidence the potentialities on using terrestrial photography as approach. During this contribution, we performed a survey concerning the cameras available in Svalbard, and we found, let's say, a lot of cameras. Different institutions are involved, and we prepared a survey with a questionnaire that is still ongoing. Here the link, and everyone can contribute to this survey. During the survey, we found at the moment about 60 cameras that are managed by different research institutions, and of course also by different private companies. In order to have a clear picture about these applications, we prepared a metadata description concerning the localization mainly, and secondly on the image processing and on the camera setup. We prepared a chapter for the last SESS report. We received the contribution from 4 different nationalities, 8 SIOS members and 8 not SIOS members. The final output is available on the SIOS data catalog, and of course you can ask for information about the different cameras identified. Concerning the data processing, we investigated what kind of procedures we are looking at in our systems, and the idea is to find a way to standardize this kind of workflow in order to have a shared approach. We focused our attention on the most, let's say, high maturity level datasets. These devices are operating since a long time in the Ny-Ålesund area, in the Adventalen area, and in the Örnsköldsvik area, that could be targeted as a reference site for this kind of approach. For example, in Ny-Ålesund, there is a time-lapse camera operating from the Zeppelin Observatory, managed by the Norwegian Polar Institute, and we analyzed 300,000 images in order to have a long time history, a time series from 2000 to 2020 at the moment, and we combine different perspectives. For each year, we can describe a melting season with a specific snow seasonality, and we can retrieve significant information that in the future could be combined to the ones that you have seen before in the previous talk. Similarly, University of Oslo described this kind of seasonality and started to make some comparison with the satellite products, MODIS, Landsat, and Sentinel. And in later, Kristoffer will show some other application. In Örnsköldsvik, the Institute of Geophysics tried to retrieve information about the hydrological processes occurring in Örnsköldsvik, and there are some applications focused on the vegetation phenology. That similarly is investigated in the Adventalen area by the University of Tromsø. In that case, they are not looking at the white, let's say, how much snow is on the ground, but how much green is on the ground, so the opposite, but the information is more or less the same. This approach, the one based on terrestrial photography, can give us a lot of information, not only on the snow cover, but also on different for different other disciplines: hydrology, glaciology, optical remote sensing, microwave remote sensing, atmospheric sciences, ecology, and some application on the coastal areas. And we strongly recommend to consider that if you are looking about information for one of these disciplines, maybe you can retrieve information for the others. The final recommendation we defined for the SESS report is to continue to survey this kind of application, to promote the creation of a network operating in Svalbard, potentially to have a shared procedure, and to promote the use of this kind of information, since could be a way to have a continuous ground truth without having people working on the ground. So especially during this period, this could be an important resource. The survey is still ongoing, so please consider to contribute to this initiative, and we are ready to give you more details in case.
So yeah, I've been asked to present our chapter to this SESS report, of which we've heard quite a lot by now. And we worked on a topic that we have called scientific applications of unmanned vehicles in Svalbard. And of course, this work was done by a lot of different collaborators and me. So yeah, first of all, thank you for all of your work. A little bit about myself. My name is Richard. I'm a postdoc at NTNU, working part-time at UNIS, and my specialty is drones on the Arctic. And kind of the mission that I've been following for some time now is to help other scientists and different science fields to kind of elevate their research and bring it airborne and use drones in different fields. So it seemed quite obvious for me to look into this topic of how actually, what's actually a starting point? Where are we today? How are drones used in Svalbard? So yes, our work, again, it's this report that has been published in this third edition of the SESS report. We had a very broad international collaboration with a lot of different people from basically all over Europe. We have yeah, I'm not going to start naming everybody, but we had a lot of different viewpoints on it, which I think is very important for this kind of work because it's important to get like all different kind of aspects to it. So why are drones important in Svalbard? Well, I guess for this group, we all know Svalbard is a fairly remote place, and it's also a difficult to access place. I mean, there's just a very few roads, and as soon as you want to get out of the areas of where the research station and Longyearbyen is, it gets very inaccessible. One of my topics that I work on glaciers. We're looking at crevasses of glaciers and how to study and how to map these. And it's very obvious that these are not areas that you can reach by foot. So drones is a very natural technology to use in this kind of environments to basically to get access to areas where you couldn't go. If you want to look at this from a little bit of more of a meta view and to put it in context of SIOS and general remote sensing, we classically have these two kind of different observations. You have ground-based science, you have a scientist taking Earth observations, and then we have remote satellite-based remote sensing, which has a very large resolutions and all the problems related to that we have. And kind of filling in this gap. Traditionally, what has been used is aerial observations using manned aircraft. There's lots of examples for that, and to some degree, also very large UAVs, drones can be used. I think maybe not so much for science, but in military and defense and espionage kind of applications, that's what is being used. And still there's kind of a gap and like a gap in the low atmosphere where we've seen that a lot of smaller drones are being used. So kind of the motivation to use drones and to look into drones, which I call here UAVs, so it's unmanned aerial vehicles, is because they're a very well suited tool to kind of fill this gap between the ground observations and satellite-based remote sensing. So when we set out the work, the first thing that we wanted to inventorize is like, okay, so what kind of drones and unmanned systems are there? And then we saw that there's a lot of different things. There's this kind of quadrocopters, there's bigger aircrafts, and since we started looking into this, we also thought let's look what is on the other end of automated systems. Let's look at some marine systems as well. So we also made an inventory of what kind of not just aerial systems that are used, but also marine and submarine systems. I'm not going to talk too much about them today because that's not my field of expertise. But if you're interested in that, have a look at our report. It's definitely outlined there. So just very briefly to make sure that everybody's on the same page a little bit on this. So there's like two different main types of drones, right? It's like fixed wing drones. Fixed wing drones are basically small airplanes. They've been around for a fairly long time, like hobbyists and model airplane people have been using these. And these fixed wing aircraft, their advantages, they can fly for very long distances. They can fly for quite a long time, like sometimes hours on end. The disadvantages is that they're very difficult to fly. It takes a lot of skill. It takes a dedicated pilot with like lots of experience to fly these. It's kind of difficult to let them start. It's kind of difficult to land them. It's a lot of complexity that comes with the use of them. On the other end of spectrum are so-called multicopters. These are typically very easy to fly. You can vertically take off and vertically land. You can put all different kinds of sensors on them, although they are usually limited in their payload, much more so at least than a fixed-wing aircraft. But they're very easy to fly. And especially these off-the-shelf commercial drones like type DJI Mavic, DJI Phantom, all of these, they're extremely easy to fly, like so easy to fly that basically a child can fly it. So yeah, they're easy to fly, but they're very limited also in how far they can fly. It's typically just a couple of 100 meters. Also the duration is very limited, usually like around 20, 30 minutes, depending on the conditions. And just to add this, recently there's a new kind of addition to these UAV families or drone families, which are hybrid aircraft. So aircraft that are able to start and land vertically. So they have the advantages of the multicopters, and as soon as they're airborne, they can fly straight like a manned aircraft. And yeah, as you can see in this picture here, it's pretty much exactly how these look like. There's like a couple of rotors for starting and landing, and then the wings that take over as soon as you're in flight. Okay, coming to this actual work, what is this report about? What did we do? What we did is we did basically a literature search. We just did a survey. So we went online and we hit up all the regular databases and Google Scholar and whatnot, and just try to find combinations of the words of Svalbard, Spitsbergen, and so on, together with some kind of unmanned system or drone or UAV and so on and so on. And we try to map out everything, and then we did like a meta-analysis where we try to classify this information. You know, which discipline was it used, where was it used, what systems was used, what was the kind of the product, and then we try to kind of look at the results and kind of analyze them. And we got like 45 entries into our database, and I'm going to just present you just like some of the interesting findings that we saw from these. So the first thing that we tried to identify, okay, so who is actually the users? In which fields are these being used? So this is the result of what you can see here. And I think there's two things to be seen from this. The first one is that there's a lot of different kind of uses for it, right? Geomorphology, ecology, atmospheric sciences, oceanography, glaciology, snow scientists, but also cultural heritage, sea ice. So it's a quite wide spectrum. So that's one thing. The other thing that we can see is that, okay, so the geosciences for geomorphology, kind of ecology, they seem to be very strong ones, also atmosphere and oceanography. Oceanography, of course, this was mostly the unmanned on autonomous marine vehicles. But basically what we found from this is that, okay, so there seems to be some users who kind of, you know, some fields that use it very widely, but in general, it seems that drones can be used for a very wide range of applications in the Arctic and in Svalbard in particular. So then we started looking, so, okay, what kind of type of drones are being actually used? So this is what we got from that. And basically what we saw is that there seems to be very strong, both the multi-routers and the fixed-wing drones are both quite strongly used. And these AUVs, ROVs, ASVs, these are the marine vehicles. But what we kind of saw is that when you look at the UAV multi-rotors, most of these are actually these off-the-shelf commercial drones that I talked about. So this type DJI Phantom, DJI Mavic, the ones that you can buy for a couple of 10,000 krona and just like use them without anything else. At the same time, we also have quite a lot of people who use the fixed wings and also the marine vehicles, which take a lot of more sophisticated infrastructure and know how to use them. So there seems to be like some very specialized users who use the fixed wings, and there seem to be quite more casual users, which are using the multi-rotors mostly. And what are they used for? Well, what kind of products are there? And this kind of explains a little bit of who uses them. So basically, some are used for in situ measurements, especially for the atmospheric ones. And then especially all those geomorphology guys, they've been using it to create maps. And actually, a lot of people are using them for maps. So DEMs, these are digital elevation models or digital surface models. And then these auto mosaics and maps, this is basically all the same product. You use a drone, you fly over an area, you take a lot of pictures, and then you generate a 3D model of this area, a digital elevation model, basically. And you can also populate this with pictures, and you get like a 3D map which can be used to, I don't know, like look at crevasses. That's what I did. Look at coastal erosion. Look at changes in geomorphology, and so on. So kind of again, the summary that we got from this is that like a lot of people are using these off-the-shelf products for this aerial photography. And there's a lot fewer missions that are using these fixed wings with sophisticated sensors. And this is typically people have been using this for a very long time. So next things we try to look into is kind of when are these being used and like what's the time evolution about this. And you can see that the first use actually goes back to 1998. So it's actually quite a long time ago, but it's very clear that it's only within the last 4, 5, 6 years that the use of drones has been started to increase. And I can say that the numbers for 2018, 2019 seem kind of low, but they're actually not. It's just like the publications haven't come out yet. And actually we did like a checkup, and within the last 7 or 8 months, there's at least, I think, 50 new publications that have come out that use drones in field works that has been conducted in 2018, 2019. And then we also looked at the spatial distribution to see like where have most of the studies been used, what is here the potential for like, doing long-term measurements, establishing kind of timelines. And what we see here, and this is not surprising, is there's a lot of kind of hotspots. Of course, hotspots around New-Ålesund, hotspots around Longyearbyen. There is also kind of a hotspot around the Polish station in Hornsund, but they haven't published so much, so that's why they don't show up here. But we know that there's a lot of publications in the pipeline, several of which have been published only in the last couple of months. So that's why they're not up here. So there's a lot of hotspots. Most of the studies are, again, because they use these off-the-shelf drones, are focusing on very small areas. And so far, there's no long-term measurements established, but the potential is definitely there. So I have to run back into the wind tunnel, so I'm coming to an end and just giving you the summary. So what did we learn from this report? What's the main takeaways? So first of all, that unmanned aerial vehicles, UAVs, they're an emerging technology still. They seem to have a very wide benefit to be used in almost all fields of Arctic sciences. And one of the recommendations that we gave to SIOS is that we should work together to encourage new users and new applications to get started. And the barriers are very low. Again, using an off-the-shelf drone, it's like 20,000, 30,000 Norwegian krona, 3,000, 4,000 euros. Very easy to fly. There's some things to know about it, but it's very easy. And SIOS should encourage new users to try this technology. And the second thing that we saw is that again, most of the operations are very simple, and few people use it for sophisticated missions. And the second goal should therefore be to also, look at the people who are using them drones today for simple missions. What can we do to assist them to get more out of the existing missions? What can we do to expand activities to build more sophisticated solutions? So this is basically the main summaries. Just to give a little bit of outlook, what are we working next? I think I can say that we got the possibility to make an update on this chapter, and in that we're going to discuss a little bit more of the challenges that UAVs encounter in the Arctic. There's problems with GPS, there's problems with low temperatures, bad weather, high winds, and this should not be forgotten, also legislation. There's new rules, EU-wide rules for drones that have been released this year, or which are going to be valid from next year on. And we're going to discuss these because they are kind of a barrier that you have to get over. And it's important that people have a good understanding of them. So yeah, that's pretty much my presentation. And I think we have maybe 1 or 2 more minutes for questions.
Okay, welcome back. And I will chair the next section of the session, SIOS success stories from the SIOS supported activities. So I would give you a brief introduction about the SIOS InfraNor project. I understand that most of you know about it, but we have international participants who might not know about the SIOS InfraNor project. And I would give you a brief introduction, and then we have 2 talks which highlights the success stories from this project. So the SIOS InfraNor project is being implemented to fill the gaps in the observing system. It is funded by 2 agencies. One is the Research Council of Norway, and the second is Norwegian Space Agency And there are around 41 project items, about total funding about 110 million kroners, Norwegian kroners. And this is the first major investment in research infrastructure coordinated by the SIOS Knowledge Center. The project period is from 2018 to 2022. And then the operational phase is until 2027, when the infrastructure will be maintained, or the processing chain for the satellite data processing will be maintained into this. And finally, these products and the infrastructure data derived from the InfraNor will be integrated into the observing system for the benefit of all the SIOS users. So in this figure, you can see the planned activities or the infrastructure under the InfraNor project. And I think you might have heard more about the Dornier in the yesterday's talk, and today about the UAVs. And also there are some infrastructure using the in the atmospheric mooring and the land module. And there are some products based on the satellite remote sensing, which I will focus on this talk. So the primary objective of this InfraNor project is to operate a multidisciplinary and state-of-the-art observational system in Svalbard for marine, terrestrial, and atmospheric research. And secondary is to, together with the international partners, systematically construct, develop, and maintain an observational network for Svalbard. So with this, I would more focus on the InfraNor and its relevance to EU Copernicus program. And I would focus more on the 11 projects that are closely related to European Union's Copernicus supported projects by NORCE. And these are the projects implemented by the NILU, NORCE, Arctic University of Norway, and Nansen Center. So some of them are the NORCE-funded projects. 11 projects. I would quickly go through them. It's a Pandora spectrometer, which is installed in Jolsen. Then remote sensing of snow and avalanche activities, or the CalVal of the snow parameters. You might have heard about the Hann stock. This also belongs to these two activities. Then we have the calibration and validation of biosphere sites for the generating the vegetation map. Then we have the solar elevation and phenology corrected clear sky Sentinel-2 mosaic, which will be produced annually. Then upgrade of the ionosonde antenna, and also we have the satellite-based SAR wind retrieval by Nansen Center, and the chlorophyll concentration in fjords and the ocean using MODIS Sentinel-2 and Sentinel-3. So with this 11 items, I would give briefly some of the status of these items. So first is the Pandora spectroradiometer, which is also installed in 2019 in Sverdrup station in New-Ålesund, and it is set to measure the nitrogen dioxide, ozone, and the formaldehyde. So the important thing about this measurement is it is the fiducial reference measurement for the Sentinel-5P satellite. And it is also part of the global network called Pandonia, which are under which the Pandora instruments are distributed in over 50 locations around the world. And it's a growing project. The second is the chlorophyll concentration. So this is one of the examples of this Sentinel-3 based chlorophyll concentration in fjords and in and around Svalbard. And this is important because Sentinel-3 provides up to 5 observations around Svalbard per day and at the 300-meter resolution. And these products are being generated and yet to be harvested into SIOS data access point. Again, we have the high resolution wind from the SAR data. That is the routine processing chain for high resolution wind products for SAR is in Svalbard region has been set up. And it is mainly using the Sentinel-1 images, Sentinel-1 data, and the algorithm is C-mode. So if you are interested, you can access this datasets from Nansen Center at the moment, but these datasets will be harvested into SIOS data access point. So it's basically the development goal is to integrate different types of wind information using the SAR spectrometry and models and in situ datasets. Then I would not go into details into this slide because it is already covered by Hannah in her talk. It is about the production of the snow cover fraction for entire Svalbard archipelago from 2000 to 2019. And this data set is also available now, and one paper has been published under this in SIOS special issue. If you are more interested into that, you might go through the paper. And apart from these products, which are funded by Space Agency, the InfraNor also has the hyperspectral sensor on board Dornier, which, and I think most of the parts were covered yesterday by Agnar's talk. But in continuation to that, I would like to again remind those who are joining today for the conference, the hyperspectral remote sensing training course, under which we will train the next generation early career researchers to process the hyperspectral data, which is being acquired by the Dornier aircraft. And in addition to that, we will also cover some of the topics to generate the biophysical variables using PRISMA hyperspectral data, and some of the activities from the Italian Space Agency to cover some basic lectures on the hyperspectral data. So in addition to that, we will also have a few lectures on the calibration and validation activities using in situ measurements, and then how to use the in situ hyperspectral measurements with the Dornier aircraft, and also to calibrate the satellite-based hyperspectral data. So if you are interested, or if you know some of the potential candidates who can join this training course, it's online, and the application is open until 30th of June.
So the title of my presentation is actually Towards a New Vegetation Map of Svalbard based on Sentinel-2 data. And this is actually an announcement that the work is going on, and at the moment I will say that it's more or less in the finalizing stage. During the process, a main focus have been to develop new methods for creating large area vegetation maps, and to evaluate the maps again, the satellite-based maps against traditional or conventional vegetation maps. And during the whole process, I've also searched for different types of improvements in the map creation process. The long-term goal is actually also, when the map have been created, to compare this map with a vegetation map being produced based on Landsat TM data, which was published in 2012. And that map was mainly based on data around the year 2000. So here we have a possibility actually to compare data over a 17 years span. The vegetation research activity on Svalbard has mostly been focusing on recording the distribution and occurrence of different plant species, but in some areas also traditional maps have been worked out. One main problem with these maps are that they are quite old-fashioned. They was mainly produced during the 1980s up to the year 2000. So they are more than approximately 30 years old, these maps were produced as a part of this an international research project, and the areas colored here in red is actually describing where we can find traditional vegetation maps. we have such maps here in Reinsdyrflya, Brøgger Peninsula, in Adventdalen, Edgeøya was, there was, in Edgeøya we have something called an ecological vegetation map. And also some recordings here in the northern parts of Barentsøya. So there are some maps that can be used as ground through data when I've been evaluating the satellite-based vegetation map. Another type of maps that have been produced for Svalbard is what we could call maps displaying zones, vegetation zones and sections on Svalbard. This one is from 1986, produced by Ingvar Brattbakk and published by the Norwegian mapping authorities. Arve Elverbakk produced also an overall map displaying the 15 dominant vegetation types on Svalbard, and that was published in 2005. And as I mentioned, I myself produced vegetation map based on Landsat TM ETM data with a resolution of 30 meters. So there is something actually to compare the new map with. When dealing with vegetation mapping based on optical data, we record actually the reflectance from the ground. And this reflectance varies actually in the different part of the electromagnetic spectrum. If we look at the green vegetation, we have a peak in the green part of the green visible part, but we have much more information actually in the near infrared and also in the mid infrared part. So that information is actually used when we work with optical satellite data. In this project, I've used Sentinel-2 data from two different dates, actually one from 31st of July 2017, and second one from 2nd of August 2017. I'm not going detailed into the specification of the Sentinel-2 satellite. When I do the classification of the satellite images, this can be, the first stage is actually to select out what I call a master area. And this area is evaluated quite detailed with respect to spectra. I do the first order classification in that area, and then I evaluate the product with spectra analysis, separability analysis, and based on this, I work out a first order interpretation of that map. Later, I start with mosaicing the neighboring images into this master area. In the post-classification stage, I use different types of ancillary data to in order to analyze the pre-classified product. And finally, I standardize the final vegetation map and describe it with botanical terms. So here we actually have the vegetation map that I have created for all areas of Svalbard. As I mentioned, I've used two dates. The 2nd of August was a wonderful day on Svalbard, and we had actually 3 passes of Sentinel-2A and 2B over the the archipelago at that day, and more or less all areas was covered for that single day. But I've used also data from the 31st of July in areas where I had small cloud distortions. So the resolution for the whole vegetation map is 10 meter, and the master region was, I selected the central part of Spitsbergen as a master area, because in this area we have quite a lot of ground through information. I used automatical classification based on K-means algorithm in the classification process. And in the first stage, I separated 35 spectral classes in the product. Later, this was aggregated down to two versions of the vegetation map, one with 23 and the second with 14 map units. So here we have a subsection from this overall map from Adventdalen. I can't go that detailed into the interpretation of the map, but here in the valley floor we have swamp and wetland vegetation. Here we have this very rich marsh vegetation. We also have different types of heather tundra vegetation and sterile river fans. We can also go deeper into look at the NDVI for the selected classes, and the NDVI gives an impression whether the unit is rich fertile vegetation or if it is more or less non-vegetation. Non-vegetated. I've also computed the water index, and as we see from this index, sea and oceans have the highest values here. The same is the case actually for the glaciers. So we can use the spectral information in the different channels to work out the dendrogram reflecting the spectral similarities or dissimilarities between the different classes. This is quite important actually in the interpretation of the classes. And we see that class 13, which is the glaciers, are the most different from the remaining material. So this is a quite important part of the interpretation process. Then we can look more at the products. Here we have a subsection from the Sassendalen area. Again, the rich marshes in the valley floor, the swamp and wetland vegetation here. And here we have this the heather tundra vegetation. In this case, with the dense canopy layer. And then we can put the map into a digital elevation model and see how it looks like actually from the space, more or less. Here we see into the Sassendalen Valley from northwest, and we see that the vegetated land is more concentrated, actually mostly to the valley floor. Here we have Sassendalen, a view from southeast. I've also been looking at or compare this map to a traditional vegetation map from the Gipsdalen area. Here we have the traditional vegetation map from 1990, published by Elven et al. And when we compare, the features in the landscape are not fully equal, but quite reliable. When the map is of the whole Svalbard is there, we can differentiate the area into different subregions and compare the map units in different areas. Nordaustlandet is characterized by the glaciers, 76% of the whole area. The same is actually the case for Spitsbergen, northeastern parts, this one. While the central part of Spitsbergen has obviously the most varied vegetation with different types of vegetation communities. And here we see that the glaciers only constitute approximately 16% of the overall area. So when we summarize this, the whole Svalbard constituted of approximately 11% of vegetated land, 25% of bedrocks and gravels. In the map product, I have 4% shade effects, and the glacier constitute 59% of the overall area. So to conclude, we can say that we can create quite reliable vegetation maps based on Sentinel-2 data, and by putting the different tiles together, we can create a large area map covering all areas of Svalbard. And from this product, we can look at, we can create maps displaying the overall scales of reflecting the zones and sections of Svalbard. We can work out in maps with intermediate level reflecting the landscape features, and we can also go down and to display the community type level. I've also compared these maps with traditional vegetation maps from different areas, and I have found quite high correlation actually. And what's important actually in the future is that to use this vegetation map together with other research areas like reindeer range management and geese research and so on. What I have experienced actually during this process is one of the main disadvantages with the Svalbard area, and that is actually the lack of updated field recordings. So I hope in the near future that SIOS can play an important role in this context in the years to come. So thank you.
Really nice. Thanks for the introduction. So this presentation is about the use of remote sensing to investigate permafrost processes in Svalbard, and in particular in that specific case studies, permafrost landform forming on the mountain slopes that are called rock glaciers. So this the study focuses on comprehensively mapping and documenting the movement rate of rock glacier. But probably some of you are wondering, or why do we care actually about rock glaciers, and what is a rock glacier also? So a rock glacier is an active landform located in permafrost region. When the rock glacier is active, it is located in permafrost area, and it consists of a mixture of ice and rock, and they are creeping down the slope at a variable rate, and this rate depends on climatic conditions. So several research showed evidence that rock glacier tends to accelerate or like creeping down faster when the conditions are getting warmer. And so they can actually be used as an indicator of climate change. And one also interesting thing is that it has been studied, especially in the Alps, European Alps, that rock glacier display a concomitant or similar regional behavior, which means that relatively independent of their actually absolute velocity, the relative velocity change, and this is what we can see on this graph, it occurs at the same time and in the same proportion for different rock glaciers within the same region. So this is an example from the permafrost monitoring system in Switzerland, where all the lines are from different rock glaciers and they show a relative similar trend. So based on this conclusion or previous conclusion, a project started to use rock glacier kinematics as an associated parameter of the essential climate variable permafrost. And this project is part of the CCI permafrost initiative. So it's a climate change initiative funded by the European Space Agency to use satellite remote sensing to develop products that can upscale the investigation of rock glaciers, generate inventories at the regional scale, and then monitor the movement rate all around the world. And in this project, we had like 11 different regions all around the world, and us in Norway, we are responsible for the 3 Norwegian study sites, 2 in northern Norway and 1 in Svalbard. And also, I would like to mention that this also has been supported by an action group from the International Permafrost Association working on the similar topic, inventorying and studying the kinematics of rock glaciers. So for this purpose, as a goal is to document the movement rate at large scale, we use a technique called synthetic aperture radar interferometry based on Sentinel-1 radar images. And I will not go into detail, I don't have the time, of course, but the principle of INSAR is to document movement by comparing images taken at a different time. And the movement that can be detected is only along the line of sight. So along the, it's a distance change between the sensor and the ground. So it means that to document comprehensively different slope orientations, we need to combine results from different Sentinel-1 geometries, ascending and descending. Oh, sorry. And based on this, and we actually generated many image pairs, hundreds of them, and with different time interval between the, the images in order to provide different detection capability of the ground movement. And then the results are classified in velocity classes to summarize information relevant for rock glacier kinematics. So at the end, we get a kind of a really simplified mean velocity map. And in parallel, the University Center in Svalbard has created a new, that didn't exist before, inventory based on morphological evidences or morphological interpretation based on orthophotos from Topo Svalbard of all the rock glacier in the study areas. And then we combine these two information, the geomorphological information and the kinematic information. So this is the study area. It's something around, so it's more or less the whole Nordenskiöld Land. Something like 4,000 square kilometer of land. And here we have the geomorphological inventory. So the result of the work at UNIS to identify and delineate and then characterize which type of rock glacier we can see. So you have rock glaciers that are connected to glaciers, but are not anymore, at least glacier flow, but that were derived from a glacier, and you have periglacial rock glaciers that are formed under a talus slope. This is in Rendalen, and this one here is in this little valley here, or not that little actually. And so, in addition to just delineate, UNIS has also characterized which type of rock glacier it is based on the new standardized guidelines made by this action group from the International Permafrost Association. So here we classified under 4 types: talus connected debris, mantle connected, glacier connected, and polyconnected, which is a when it's in between, it combines several spatial connection. And so our part at NORCE were to provide the kinematic information from INSAR. So this is the result of this classification of based on ascending and descending Sentinel-1 INSAR, classified with these 5 classes of velocity. This is also something that has been internationally standardized. So each study areas around the world are using the same classes. And you see here, it's everything that is moving. So it's obviously not only rock glacier, and you have a lot of processing in the flat areas, which is related to soil subsidence during the sowing season. So the active layer sowing and the ice that is melting into the ground that lead to a subsidence. We are obviously not interested in that for this specific project. So we basically extracted the information for all the identified rock glacier over the whole area. And here, just to show you an example around Longyearbyen, because at a large scale, it's a bit impossible to see how it's looking. And you have here the information about the distribution of the moving areas on the rock glaciers. And the one finding is, of course, that the rate is pretty variable, depending on the landform and also the talus or the glacier spatial connection. Typically, it's faster when it's glacier connected, because we'll not go too much into detail. You can ask me after. And then another thing that has been standardized by the international community is to finally document in terms of order of magnitude instead of velocity classes, for different reasons that I can explain also if you're interested later. So we document centimeters, decimeter, meter a year of general order of magnitude velocity. And so the final inventory looks like that, where we identify all the rock glacier and we can classify them by velocity range in a way. Yes, so to summarize, this is a really new thing in Svalbard. It didn't exist before, an inventory of rock glacier that was comprehensive and not least an inventory with kinematic information. And this is interesting because it will potentially provide better understanding of the distribution and the behavior of creeping permafrost landforms. And also we can start to discuss also the different behavior between this kind of landforms that are pretty different than this kind of landform, even if both are considered or are mapped here as rock glacier. So that will give some new research potential in the future, I believe. And so the next step is something that we also have started and will continue in the future in the framework of the CCI permafrost group, is to develop these regional indices of rock glacier kinematics to document the evolution of mountain permafrost. So for now we have generated time series. So now in this presentation, I just show you like mean velocity, but it's also interesting to extract the velocity in time and the variation of the velocity during the season, but also interannually. And then based on this, we could average for each season and then extract several of these time series on many rock glaciers and provide this kind of regional indices. And then the idea is to compare this for all the regions we selected around the world, and maybe several others, because it's of course not covering all the mountains for now. So that's a bit of the future plan. And that was it.
I'm going to talk about how we can retrieve fractional snow-covered area from satellites using data assimilation. The outline of the talk, I will first kind of motivate why we need data assimilation for cold region science. I will give an overview on some previous work we've done with data assimilation and Earth observations. And then I will present a new approach to spectral unmixing applied to snow cover. So first of all, starting with data assimilation for cold region science, we have all this lovely Earth observation data. This just shows some of the Earth observation data I've worked with. So we have MODIS, Landsat, Sentinel satellites, we have the Planet CubeSats, we have airplanes, we have now drones as well. So isn't this enough? Why can't this Earth observation kind of speak for itself? Why do we need to add something else? Well, usually these don't directly measure what we're interested in. They contain gaps in space and time. They have a limited coverage. The measurement uncertainty needs to be accounted for somehow. There's also usually a mismatch in scale between what they measure and what we're interested in. And these data are often already some form of retrieval or model product, actually. So a way to solve these problems is to use probabilistic inverse modeling. And when doing that, we use physical models that we look at as kind of forward or data generating models. And then we try to invert those models to go from what we observe to the things we're interested in. So it turns out that a really nice way to solve inverse problems is using something called data assimilation, or what we in the geosciences call data assimilation. This essentially uses Bayes' rule to go backwards from the observations to the states that we're interested in, and probability theory. It's important to emphasize that here we use probability in the sense of a measure of epistemic uncertainty or belief, and not frequency, as many people would usually refer to probability. And in this way, we can constrain models with data, and we can also add value to data. And this is a bit different from machine learning. In machine learning, you actually try to fit the whole model, and you forget about most of the science that you knew from before. So in simpler words, Bayesian inference lets us reason about things we can't or imperfectly observe using things that we can observe. I put an example here, but I probably don't have time to go through that. Data assimilation is then basically the application of this kind of Bayesian inference to mechanistic modeling. There are many different techniques that you can use for Bayesian inference. Here are some of them. I've mainly worked with particle methods, ensemble Kalman methods, and Markov chain Monte Carlo methods. In this talk, I'll go through a little bit results with the first two. Here's a brief overview of the work we've done assimilating Earth observations. The motivation here is this big unsolved problem we have in snow science, which is basically that it's really hard for us to know how much snow water equivalent there is and how it's evolving. But satellite remote sensing is a really essential part of solving this problem. So in my PhD, I developed a reanalysis method which combines physically based snow models with optical satellite data and data assimilation to try and get better estimates of SWE and other snow variables. This is based on older work by a bunch of other people as well, and we've applied this to areas in Svalbard, the Swiss Alps, and California, and also now recently Lebanon. Here are some results from Lebanon. This is a paper that's currently under review, hopefully about to be published. On the left, you see the observed snow probability from MODIS. In the middle, you see the snow probability that we get in our model after doing data assimilation. And on the right, you see a scatter plot showing that the two agree well. Here is some work we're doing to look at future snowpack. So we can actually use these reanalyses of the current climate to bias correct future climate projections and get a better idea of what will happen to the snowpack. This is about to appear in GMD. I've also, as I said, done this in California. So here are some results. In the top panel we see the fractional snow covered area during the melt season. Red is before data assimilation and blue is after data assimilation. We consider a bunch of different satellite data. The important thing is what's happening in the bottom panel, where we see that the independently observed SWE, we are better able to capture that after assimilating the optical satellite data. So we're also doing this as part of the permafrost CCI project that was mentioned in the last talk, where we're using this kind of technique to bias correct the snowfall that we get from our meteorological forcing. So we've done some tests now for Svalbard for the last 20 years. So this shows the fractional snow covered area before data assimilation, then after data assimilation. Doesn't look like there's a big difference, but if we look at the scatter plots relative to MODIS, we see that the blue lines are much closer to the one-to-one lines, which is what we want to see. So this also then leads to nice updates in the SWE, which is what we want, and some preliminary validation. If left is before data assimilation and right is after data assimilation, suggests that this helps us better to capture what's actually going on with the snowpack. We're also working on drones because that's been mentioned. I just put that out there, but I don't have time to go into that. So now for the exciting part, this is a new approach to spectral unmixing applied to snow cover. This is building on a previous study where we have a camera installed on a mountain close to the Ålesund. And using this camera, we can get really high resolution snow cover maps that we can use to validate satellite retrievals. So there are typically three ways people get snow cover. Either they use the normalized difference snow index and a threshold. This is very biased. I would not recommend doing that, especially for coarser resolution satellites, but also for higher resolution satellites. You can also use regression, but in my opinion, the most elegant approach is spectral unmixing, where you assume that each pixel can consist of a linear combination of many different surfaces. Each surface has a different reflectance spectrum, and you see what combination of those reflectance spectra produce the observed reflectance, and in that way you can get a good estimate of fractional snow cover. So this just shows in the bottom middle panel, we see the fractional snow cover estimates, and it looks much better than the other two estimates to the left and right of that. This is some validation from the paper I mentioned. I won't go into detail, but basically this shows that the best performing method compared to a bunch of different methods is the spectral unmixing. And this regression approach is okay as well, but spectral unmixing is the best approach. So why is this a problem? Well, the classical approach to spectral unmixing, which basically uses optimization and is used operationally in the ModSCAG and TM-SCAG product. It requires optimizing over snow end members, and it's costly and difficult to parallelize. It can converge to the wrong solution. There's a bunch of ad hoc stuff in the algorithm. It's quite slow, especially for high resolution imagery, and there are no uncertainty estimates. So what I propose is to use this Bayesian or data assimilation technique where we basically say, okay, this is an inverse problem. We know how to solve inverse problems. We use Bayes' theorem, and we have these particle and Kalman methods that I mentioned before that can do this quite efficiently. The advantages with this are that it allows for a mixture of snow end members. We get uncertainty estimates. It's potentially faster. It deals with constraints quite elegantly, and it might also be more accurate. So here are some preliminary results comparing the camera to Landsat fractional snow-covered area retrievals. Top left, we see the classical spectral and mixing approach, and then there are a bunch of different approaches based on data assimilation. We see that the approach that performs best overall is this algorithm I've called PIES, which is the particle iterative ensemble smoother. It's a mouthful, but PIES is easier to remember. And it performs a little bit better than the classical approach, but it's much faster, and it also provides uncertainty estimates. We can do the same for Sentinel-2. Here I'm missing one of them because I didn't have time to finish all the runs. But again, this PIES technique is the best overall. Now you can say, oh, this is just a tiny area. What does that have to do with anything? Well, this area is quite typical of large parts of the Northern Hemisphere, I would argue, but we can definitely scale this up too. So this is the same thing applied to the whole Bregger Peninsula. This is this PIES algorithm. Here we see fractional snow-covered area on the right, and on the left is the false color image from Sentinel-2. This is at 10 meters resolution, so we actually get the fractional snow cover within each 10-meter pixel. In addition to fractional snow-covered area, we can also get snow grain size estimates. That's on the right here, which we can use to derive snow albedo. So this is actually really useful also for climate modeling. Yeah, so these are just some different dates here. This is a bit later in the year. Again, we can also look at grain size. The white areas here don't contain any snow. That's why they're like completely masked out. And then we can look at an even later period where it's mainly the glaciers that are still snow covered. And again, the grain size. And then finally, to speed this up even more, we can do this Bayesian solution on just a small subset of the pixels, then like 1% or so. And then we can use that 1% of pixels to train some function approximation like a support vector machine, which can then roughly estimate the snow cover for the pixels that we didn't train on. And this works okay, but it's also maybe 100 times faster than the normal approach. So I think that's it. And I'm happy to take questions in the chat if there's time for that. Thank you.
Okay, I couldn't see what you guys see, but now I can see it.
Everything looks good my side. And well, it's 20 to 5, 20 to 6, I should say, Norwegian time. So welcome back, everyone, for the final session of today. To start this last session, we have Isabel Ishkid. I'm really sorry if I really mispronounced that. And she'll be talking to us today about disturbance detection and classification with UAV images. Isabel works at the Norwegian Polar Institute and Aarhus University. So Isabel, do you want to take it away?
Yes, thank you. Yes, my name is Isabel, and I'm a PhD student at the Arctic University of Norway, but I'm also collaborating with the Norwegian Polar Institute and Aarhus University. And my PhD is part of the COAT program, which stands for Climate Ecological Observatory of Arctic Tundra. And here I'm going to present you a study that is almost ready for submission for the SIOS special issue. It's a study we conducted on Svalbard. And what we try to do here is we try to develop methods to use UAV images to detect disturbances and state changes in vegetation by using classifiers and see if we can actually integrate this into ongoing monitoring programs. No, I just have to, it's not switching over. Now it is. Okay, I have to multitask a little bit here. So before I go into my study, I want to talk a little bit more about COAT, because COAT is a part of the COAT Svalbard is a part of the SIOS terrestrial program. It's an integral part of it, but COAT also exists on mainland Norway, and it's looking at monitoring changes in climate and relating it to herbivory management in the Arctic tundra. CORD is an adaptive monitoring program, which means that it's hypothesis-based and based on conceptual models. So it's trying to move away from trying to monitor everything, but rather have concepts of things that may change in the future and how things can change with respect to each other, try to collect monitoring data that is scientifically sound. Adaptive monitoring means also that you can change your goals and methods over time if you've learned new things on the way, and it's very open to the integration of new technology. And this is where my PhD is coming, and I have a background in remote sensing and ecology, so I'm trying to bring those two worlds a little bit closer to each other. So for this study, our sort of ecological aims are to get a better understanding of some of the state changes in the Arctic tundra on Svalbard. I don't want to go too much detail here, but it's commonly described that the Arctic tundra on Svalbard can move between a more mossy and a more herbaceous state, depending on things like temperature and precipitation. But we've published a study now that also shows that we can also move into other directions, which we call here the bare patch state. And that is a direction that can happen, for example, if you have a lot of local disturbances. And some of these things are trends that happen slowly over time, whereas other things can happen within a season or just within a few days. And this is exactly where sort of the UAV images are coming in. Some of the things we can well document and study on classical field-based plots, and some of these trends we can look at satellite data, but especially those disturbances that happen at high frequency, but in they're very small scale, but they happen sort of plastered throughout the landscape. These are the things that we try to capture with UAV images. So the disturbances or these states that I'm talking about here can be bare ground, could be mud boils, could be slumping. And two of the things that I'm particularly interested in is the impact of goose grubbing. So how geese can change the landscape. And this is images of geese that have been pulling out moss roots within the moss tundra in the spring season before they're breeding. And we have also occurrences of winter damage where there's rain on snow events or late freezing within the season. So we're interested in detecting these kind of disturbances, and disturbance doesn't mean it's a bad thing, but it's changes to the system as we see it. And we're also trying to see how, if something grows back, is it growing back to something what it has been before, or do we see, for example, ecositum, Caraxus bastacea, or biological crust emerging afterwards? For the methods, we also are interested in seeing, for us it's important to actually find a system that's working for the monitoring system. So we don't want to just have small plots here and there, but we want to see, for us, if it's actually relevant for this type of ecological monitoring, we have to cover quite large areas, which means maybe kilometer strips. So it's not covering entire valleys, but it's more than just a few hundred meters. The data quality has to be of high enough resolution that we can detect these changes, which is usually below 10 centimeters. And the tools we're using have to be easy enough to use in the field from non-specialists. So we don't have the space in our field campaigns to usually include specialist pilots. So this manuscript is also aiming at describing these things at a little more broader range that is not just specific for Svalbard. So I'm not going to go into too much detail here, but we find that there's quite a bit of information on how to do good field planning and data collection, but there's less focus so far on how to use UAV images for monitoring when it comes to variable or layer selection, ground cover class selection, and how transferable these classifiers can be. So we conducted our fieldwork in 2019. We have 3 study sites that are also part of the COAT long-term monitoring in Todalen. It's not really in Todalen, but we call it Todalen. It's close to Todalen, in Jansenhaug and Sassendalen. Each of these sites are about 1 square kilometer. And we've been using an EBX fixed wing drone, which is a very lightweight drone. It's only 1.4 kilograms, and has an ideal battery range of 90 minutes. Effective flying time is usually 60 to 70 minutes. But for us, and I've been missing that actually in the presentation earlier today as one of the options of drones that are used on Svalbard, because for us, this has been a little bit of a game changer. The small shelf drones that are lighter don't cover enough area, and the bigger multi-rotor drones for us are too heavy to bring in the field. So here's an example of how we fly this drone. it's very easy to handle, and you fly it from a PC instead of using a remote, so you don't have to have that much knowledge on how to fly. Just showing an example of us landing the drone. This is part of a winter study that we've been conducting, but it's just to show what she looks like in the field when she's up in the air. All right, so other than collecting the UAV images, and sorry, I forgot to mention, but we collected infrared data with a Sequoia 4-band camera and normal data with the RGB camera. And our work and the way the drone operates, it has a direct RTK link, so we get positions, real-time positions that are corrected already. And the Sequoia Plus camera has a calibrated sensor, so we only took spectral target pictures as backups. The same with ground control points, only were used as checkpoints, but not for the validation. For ground truthing, we collected about 15 different vegetation classes in the area by using a GGPS. And then sort of imagining a circle of about 15 centimeters around the point of the area that is, we said was that exact vegetation class. We used photogrammetry, Pix4D, on a rented external server to process our data. It was too large for our own data sets, for our own PCs. We we used the optical data from the Sequoia camera, not from the RGB camera, because we had some issues with standardizations there, because settings changed in the field. We calculate the gray level occurrence matrix to get an idea about the neighborhood values. We calculated terrain values from the 3D point cloud that we generated in the Pix4D software. I'm going a little faster here now because I'm running out of time, but we spent quite a bit of time to find variables or layers that were well describing what we were seeing in the landscape. So the way we selected the classes is that we had a set of initial classes and a list of simplified classes, and we wanted to do that in order to not be guided by our classification, but have classes that we think are important. And so we had sort of a wish list and a minimum wish list. And from those results, we generated our optimized classes. So from now on, I'm just going to talk about the optimized classes. We use random forest models or classifiers to assess our data, looking at the different the 3 different locations, and then also using only the optical information and the optical and the terrain together to see if there's any difference. And then we tested the classifier from each location also on the other study sites. So this is some of our outcomes. So before going into the classifier results, we wanted to see how well we actually detect the disturbances we're interested. And here you can see quite clearly that the NDVI values are lower for, this is in this case, bar ground, which is maybe not so surprising. But when we look at the goose grubbing, we can see that it hovers right in the middle of it. So we are working at a resolution where we actually detect this kind of things. The same for the more dry and mesic terrain. We have the Dryas and the Calciope areas, and then we have things like winter damage and biological crust that are have lower NDVI values. Distinguishing between these two has been proven very difficult, so that's ongoing future work. So we also compared the macro scores between the different runs that we're doing, and we see that the optical and the terrain values have been performing better overall. I don't have time to go into this table, but you can see that it's quite different depending on the classes, but there's some highlights. For example, we can actually detect the equisitum, moss equisitum class quite well. And this is things that haven't been tried before in this way. Looking at the transferability, you can see that it's much lower, but the Sassendown and the Janssen-Hagen model have been more similar, although weather conditions were quite different. So we think it has more to do with the way terrain looks like rather than that spectral calibrations were off. And finally, I just wanted to show you what the outcomes, the actual maps look like, and show you some highlights. Here you can see a dry terrain that has been classified quite well. And here in Sassendown B, you can see this is the bars is 5 meters. You can see areas where we've actually managed to detect the goose grubbing. Same as for this area here in Torbjørn D. Down in the bottom, it's most tundra, and then the brown is goose grubbing that has been detected. So I want to just, sorry, I'm a little over time, conclude with that for us, this has been, this workflow will be applicable for future cohort monitoring, which is part of SIOS. We've been able to generate dynamic maps that we can actually see year-to-year differences and detect those small but frequent disturbances. And then future work will be to better some of the classes that I couldn't go into now, but were classified too broadly. So we need to add some more disturbed terrain classes. And we've started to link our drone data to satellite classification to use it as a ground truthing data set.
Okay, so thank you, and thank you for following today my poster presentation. I will try to zoom in and to explain you as better as I can. So today I would like to show you my multi-sensor analysis of snow dynamics and the synthetic aperture radar signal sensitivity to vegetation growth in Adventalen. So the reason why we have focused on this topic is because the timing of snow melting and the first day of snow are considered indicators of Arctic ecosystem status, and also the period of snow melting and the snow dip have a significant impact in the definition of the phenological phases in the Svalbard archipelago. So therefore, the main goal of our project was to use a combination of SAR and optical satellite data, specifically Sentinel-1 and Sentinel-2, in order to map the spatial and temporal pattern of wet and dry snow cover. Sorry for my problem of audio. And then we also wanted to understand how polarized SAR data, specifically in the HV channel, can help to detect the growing pattern of Arctic vegetation. Our study area, as you probably know, this area is Adventalen. In the map here, you can see the 5 ground stations that we used for the validation of our products. And about our datasets, we use 115 Sentinel-1A and 1B images, and 43 Sentinel-2A and B images. We used only 43 images from Sentinel-2 because of the cloud cover. And for the 5 ground station, we used data of NDVI, soil moisture, and temperature. We processed the data for the year 2017 and 2018 for the summer season. We applied to the SAR data a frost filter, while for the optical images, we interpolated the images using the KR regression. Here you can see some the methods, the explanation of the methods. So we started from the average of 3 winter images and 3 summer images using a specific data intervals using the weather station. And then we applied a simple method, the ratio method, to optimize the threshold. We find out a threshold of -2.8 dB. And using this threshold, we created a binary wet snow mask for all the Sentinel-1 time series. Simultaneously, we used a threshold of NDSI of 0.6, and we created Sentinel-2 binary snow classification that we validated using the ground station information. From the ground station information, we use this data also to detect if the HV channel could follow the phenology of vegetation. So here you can see some of the results in the two graphs. I can try to zoom a bit. Okay. Okay, in these two graphs, you can see in the x-axis, you see the day of year, and in the y-axis, you see the kilometer square of melting snow and surface free of snow for the 2 years. In gray, you see the season 2018, while in blue and red, the season 2017. As you see from these graphs, the 2 years are different, and we found out a difference of 20 days, around 20 days, in the valley of Adventalen. Instead, this is an example of the maps that we created for each Sentinel-1 images using a multi-sensor approach. In the map, you can see in green the area free of snow. In blue, you see the area where the snow is melting, and in white, you see the dry snow. Finally, the last part of the study focused on the sensitivity of the HV channel to vegetation growth. And here are 3 examples of the data we extracted. So we extracted in blue is the HV channel, in green is the NDVI from the ground station. Here you see in blue the HV, and in red the soil moisture. And in the last one, you see the temperature. So we did a correlation for each ground station, and the conclusion of the study were that there were a high variability in the duration of the snow season for these 2 years, so for the year 2017 and 2018. In the year 2018, the snow melted earlier, about 20 days compared to the 2017, and also the surface was free of snow. From our sensitivity analysis, we found out that the HV channel showed a stronger response, so followed better the vegetation compared to the soil moisture, especially specific type of vegetation, as the areas dominated by graminoids. In these areas, we find out an R of almost 0.7. And the last results was that the temperature was strongly correlated with the HV channel, with an R of 0.74. And when the snow melt was delayed, so in the season 2017, this was more correlated with the temperature than the previous year. Consequently, this process that caused the delay in the soil thawing process caused changes in the sensitivity of HV channel to vegetation growth. So this study was funded by the University of Bolzano and Jawak Research. And the fieldwork was funded by the Research Council of Norway using 2 projects, the Snow Echo and the Sensing Echo from the Front Center of Terrestrial Flagship. So this is all of my presentation.
So hello, I'm Lukas. Thanks for having me. I'm from the Institute of Geography of the University of Erlangen-Nuremberg. And today I want to share some insights with you about our research over the archipelago by using ISAT-2, Sentinel-1, ISAT, TanDEM-X remote sensing data. So first of all, to ISAT-2. In a recent project, we used ISAT spring campaigns spanning from 2003 to 2008. and newer data from ISAT-2 in spring 2019 to compare height retrievals from both missions at their orbit crossover locations across the archipelago. Therefore, we used some scripts from NASA's altimetry processing toolkit called CAP Toolkit, which was written by the corresponding authors. You can find it for free on GitHub, and I highly recommend checking it out because it's super useful for many purposes regarding laser and radar altimetry. So what we basically did, you can see it here on the bottom left. We always took measurements of all ISAT footprints, ISAT ground tracks, and compared those to always all footprints of each ISAT-2 track, here represented by the blue dots, and calculated orbit intersections. If we found an orbit intersection, we took the height retrievals of the 2 closest footprints and linearly interpolated them to the crossover locations. And after that, we calculated total elevation change by comparing those both interpolated values, and finally calculated annual elevation change rates by dividing the total elevation change through the absolute time span between both acquisitions. To the right, you can see our measurement coverage over Svalbard, and you can see that our crossover measurements are mostly limited to the ISAT reference tracks, which made us do a common hypsometric extrapolation with polynomial fits to derive regional and Svalbard-wide elevation change rates. By looking at our results, to the left, you can see all crossover values interpolated over the archipelago with ordinary kriging interpolation. And you can see that we have a pronounced southwest to northeast finning trend with increased finning rates in Northwest Spitsbergen, South Spitsbergen, Barents Oya, Edgoya, and less elevation decrease. And in addition, large portions of the inland ice in thickening or in balance at the northeastern regions. What we also can see is that finning is happening almost everywhere across the along the archipelago at the margins. And we can also see some major surge, such as, for example, that one of the Nartra Spring Glacier system, or the very striking surge of Storestraumen or Basin 3, which happened approximately around 2012-2013. If you look to the right at our hypsometries, at the regional hypsometries, and that one of complete Svalbard, we can also see that low elevation finning is happening in almost all regions in the magnitude of 0.5 up to 5 meters per year. And we can also see that we have a diminishing finning trend at higher altitudes, but in this context with variations from just diminished finning in, for example, South Spitsbergen and Northwest Spitsbergen to a slight thickening trend up to 0.5 meters per year, for example, in Northeast Spitsbergen and Ostfona. We also calculated mass change rates by applying the common conversion factor of 0.850 grams per cubic centimeter. And if we look at our regional mass change rates, we can also see that the southwest to northeast finning and therefore mass loss trend is also reflected in the mass change rates over the archipelago. Further, our results agree well with those derived through recent research by Morris and colleagues with using Cryosat-2 radar altimetry, which likewise measured this spatial mass loss trend, this southwest to northeast mass loss trend. And if you take those Cryosat-2 results and ours and compare them with intra-ISAT measurements from Moholt and colleagues between 2003 and 2008, we can see that in addition to the West Coast being a constant contributor of mass loss, we also see like a little bit of a spread to accelerated mass loss to areas bordering the Western Barents Sea, so the eastern side of Svalbard. This is also reflected in the total mass change rates for the whole archipelago, where the Cryosat-2 results and our ISAT-2 results show pronounced mass loss in this decade compared to that one in the last decade. Moving on from ISAT to Sentinel-1. So in a recent huge project, Sentinel-1 radar images were processed by using intensity, feature, and speckle tracking to produce data sets of scene pair, monthly and annually average 200-meter velocity grids in 12 major regions outside the Greenland and Antarctic ice sheet. Therefore, about 110,000 Sentinel-1 SLC scenes, which corresponds to about roughly 450 terabytes, were processed in a high-performance computing environment at our university, which has great computational capabilities and, for example, over 6,100 gigabytes of RAM. Data was processed from 2014 up to date, and data is continuously updated every year, which is around 24,000 scenes per year. All those velocity data is freely accessible at an online portal of our university, which you can find in the link down here below. You can perform simple online analysis, view the data, and download it. And I personally think this is a huge contribution to open science, as you can, for free, access all those velocity data at the link given here down below. To show you the potential of derived Sentinel-1 products, also Svalbard was chosen as an example region. To the right, you can see surface velocity diagrams plotted against time from January 2015 to November 2020. Velocity values were calculated as the median displacement within a 500-meter buffer around 3 points of the center lines of 6 example glaciers. And if you take a look at the diagrams to the right, you can see that we achieve highly dense and continuously time series of surface velocity over all 6 example glaciers, which allows for a highly detailed estimation of short-term and long-term surface velocity fluctuations. We also compared derived Sentinel-1 products to surface velocity products derived by TerraSAR-X data and Landsat-8 Go Live and its live data. For example, here over 4 test glaciers over Svalbard. And by speaking of numbers, mid-glacier velocity offset from Sentinel-1 to TerraSAR-X was very low, even below 0.08 meters a day, which is considerably lower than our comparison from Sentinel-1 to Landsat-8 data, which has a mid-glacier velocity offset of about 0.17 to 0.18 meters a day. Off-glacier velocity comparison, or the off-glacier velocity offset between Sentinel-1 to TerraSAR-X data is even smaller, with below 0.04 meters a day, which is again considerably lower as our comparison with Sentinel-1 data to Landsat-8 data, which is roughly about 0.19 to 0.24 meters a day. And this overall shows that derived Sentinel-1 surface velocity products are a great complement to already existing Landsat-8 optical velocity datasets. Overall, to the right, you can see a surface velocity mosaic derived by Sentinel-1 data by scene pair velocity fields, over 550 scene pair velocity fields in 2019. And we can see that we achieve a very dense and smooth field of surface velocity over the whole archipelago, which allows for a wide opportunities of applications, for example, for numerical ice dynamic modeling or mass flux calculations. As I already said, derived Sentinel-1 surface velocity products are a great complement to already existing mosaics derived from Landsat-8 optical data, and in addition show advantages over featureless and slow-moving ice cap interiors and accumulation areas. And this is mainly because the speckle tracking on Sentinel-1 6-day repeat acquisitions produce generally more reliable velocity measurements than the optical data. Lastly, just a quick insight about ongoing research with TanDEM-X radar data over the archipelago. So currently, TanDEM-X acquisitions from 2010 to 2017 are processed to determine elevation change over Svalbard in this period. At those red rectangles, you can see our coverage over the archipelago, which is sufficient to accurately determine elevation change trends in this period. You can see here that up to now, we only processed some parts of the eastern side of South Spitsbergen, but those first results also show the pronounced thinning at this area of Svalbard, especially at the margins of marine terminating glaciers, with a small exception of this blue dot, which was a surging glacier. But as I said, this is our just first results, and more are expected to come soon. So in the end, I just wanted to quickly once again advertise the online portal for Sentinel-1 surface velocity data, which in my opinion is a great project from Peter Friedl, Thorsten Seehaus, and Matthias Braun, and a great contribution to open science. You can see here the interface where you can access the data. And if you need any surface velocity data from Sentinel-1, for example, for Svalbard, feel free to visit the online portal. Thank you.